reaction quotient and small equilibrium constant. Let's have a look at this question over here. We have to put an ICE table because we have moles over here, we have liters over here, so I'm going to put them in molar concentration, create an ICE table, and then you end up getting an expression, right? As you can see, this here is our expression. We assume that the ICE table has already been completed. You can try it yourself on your own. If you have no idea how to do this ICE table, see the previous video, link is in the description, which is a prerequisite to this video. Now, we're going to make an approximation rule, okay? Just because, as we can see here at the bottom, this is not a perfect square. So we have to use the quadratic formula. It's just going to be a lot of rigorous, tedious work. We don't want to be doing it if we don't have to. So we check to see how small the KQ is. As you can see, it's very, very small. So what is this approximation rule? Well, an approximation may be made if the KQ is at least 1,000 times smaller than the actual initial concentrations of either reactant. So as you can see, we're going to multiply by 1,000. As you can see, it's still a very small number. Is it lesser than this and this? Absolutely. So it is lesser than the initial reactant. What is going to happen next? So the actual change, so the C in that ICE table can actually be removed. So as you can see, this here change has been removed. As you can see what we've done over here, we're going to isolate for X. And this is our value for X. Since E, our equilibrium in the ICE table for the product of H2O is 2X, as you can see, this here is the 2X. Again, you do the ICE table on your own to see how we got 2X as our product at equilibrium. 2X, we're just going to substitute our X over here. So this is our answer for X. We're just going to bring it down, substitute it, and you end up getting this many moles per liter. Again, ICE table is going to be in moles per liter as a disclaimer. Next, QEQ has the same formula as KEQ, but it may not be at equilibrium. So what is this QEQ? Okay, we use this as an indicator to see if the shift in the reaction prior to equilibrium is going to shift to the left, to the right, or if it's going to stay the same, which means it is at equilibrium. So for example, if QEQ is the same value as KEQ, equilibrium has been met. However, QEQ being greater than KQ means that there are more products than reactants. What does that mean? This means that the products are greater in number, which means that they need to be consumed more, decomposed more, and that the reactants need to be forming a lot more to be reaching equilibrium. If QEQ is lesser than KQ, that means that there are more reactants, so those need to be consumed more so that we can produce more products in order to hit equilibrium. So QEQ, like I said, it's the same formula as KQ, so let's do that. As you can see, this is going to be our product. We have to put it on the top. As you can see, this is our reactant. We have to put it on the bottom. Of course, for our P Cl3, it has a coefficient of 4. That has to be an exponent. And then our 6Cl2 has to be also an exponent over there. We'd ignore this P4 because obviously that is a pure substance. We end up getting QEQ is greater than KQ. So of course the reaction shifts to the left towards the reactant. Please try this question on your own. Try this yourself. Pause the video and I'll be giving you the answers shortly. This is the answer.